Okay, so then we can start. I'd like to welcome you to the CiA Technology Day. My name is Rainer Zitzmann, hold a degree in electrical engineering. I'm the general manager of the CAN Automation GmbH, which is a 100% daughter company of the association. Joined CAN Automation in 2004, have a long experience in giving CAN seminars, acting as technical consultant, executing conformance testing, representing CAN Automation in fairs, conferences, and so on. So a long experience in these kind of things. And furthermore, I represent CAN Automation also in international standardization groups, for example, when it comes to standardizing the communication in light electric vehicles, accompanying charging of light electric vehicles via communication link, introduced the CAN standard in the train communication network, so that we have there a proper CAN open standard, and also to tend to the clean open standardization. Yeah, today I have the honor to guide you through this technology day. And you see here the timetable. We start with a short welcome and introduction to CAN and automation. Then I will give you an insight to the three CAN protocol generations that are now available, or maybe three and a half. And then I show you some insights to the CAN network scalability. So sometimes it's a little bit felt as complex. On the other hand, it offers us some chances. So as I've said, I will show you there some insights. Then I will hand over to my colleague, Dr. Martin Merkel, who gives us some insights to safe and secure CAN communication. After that, you have a chance to recover. And after 50 minutes, then Oscar Kaplun is presenting the CAN XL ecosystem, and the entire session is then finalized by Holger Seltwanger, the CAN and Automation Managing Director, with insights to embedded AI and CAN and the international CAN standardization. Yeah, let's have first some insights to CAN Automation. Who is CAN Automation? Why are we organizing events like that? So CAN Automation is the international users and manufacturers group that develops and supports CAN Open and other CAN-based high-layer protocols. The nonprofit group was founded in 1992 to provide CAN-based technical product and marketing information. The association fosters the image of the CAN technology and also provides a path to future network technologies. So in 1992, some people said, well, it makes sense to bundle forces and to promote the CAN. Why limit the CAN to the automotive use cases? Why not using such a robust, reliable, simple to use, and highly available communication technique in other application fields where something is to be automated? And since these days we promote the CAN, we show that it is a rather attractive candidate. And on the other hand, we assist people in using the CAN. And finally, as it is depicted here, we are bringing people together. So we are also trying to be a meeting point of the CAN community for exchanging latest experiences and somehow accelerating the further developments in CAN and keeping the CAN meeting the requirements of today's embedded networks. So, as I've already said, CAN Automation had been founded in 1992 with the objective to promote the CAN. Therefore, we have the CAN newsletter, which is still available, appears quarterly, and you can get all the information, what's going on in the CAN market, get in-depth articles in this magazine, now available as an online magazine, and you can go to these latest editions always on the CAN and Automation website. Furthermore, we organize expert conferences where experts inform others about their latest experiences, where we support and enable the networking among the CAN experts. So this format is in particular the International CAN Conference The next edition will be next year, the 19th International CAN Conference taking place in Tutzing. I will say something to that on the next slide. And furthermore, we assist CAN propagating around the globe, not only from market to market, but also around the globe. So everywhere on the globe where someone is working with CAN, needs some assistance, then we are very willing to support them. So also if you have any subsidiaries abroad, then we are willing to go there, promote CAN, explain people how to use it. Furthermore, Canyon Automation paves the ground that companies can meet together according to antitrust laws and can discuss how to overcome in a harmonized way certain CAN-related challenges. So the outcome of these meetings are then CAN specifications or CiA specifications, and we maintain them, support further development, or submit them to international standardization to increase the acceptance of these agreements, of these specifications. And you see here on the lower part of this slide that we support a lot of development in the CAN business field. And you see here in 2012, there was the presentation of the second generation of CAN, the CAN with flexible data rate, at an event organized by CAN in Automation, the International CAN Conference at Hambach-Kassel. And we also then enabled the development of the CAN Open edition that makes use of a CAN with flexible data rate, which was developed by the IG CAN Open FD. We took also the patronage of the development of the CAN XL, the third edition of CAN. So you see a lot of movement was ongoing, and while there was the development at CAN Automation of CAN XL, there were still some further developments with regard to CAN-FD, how to set up CAN-FD networks, how in a best way, how to allow very simple CAN-FD implementations. So a lot of movement is ongoing in the CAN business field. And this depicts that CAN is not just a finalized technology, but there are always upcoming new requirements with regard to embedded networking. And we here at CAN Automation, together with our members, try to keep the CAN bus meeting these requirements today and also tomorrow. And finally, we accompanied also then the international standardization process of CAN XL. So that what had been pre-developed at CAN in Automation was submitted to international standardization and is now available as ISO standard in the well-known ISO 11898-1 and 2 standard. And finally, we started thinking about embedding or modifying CAN in a way that we have a kind of Ethernetification. So how can we deeply embedded CAN-based networks into entire control architectures, which are, at least in the communication to the back office, to the cloud, are Ethernet-based. How to bring these worlds better together. This is then done in the Ethernetification of CAN. So as I've said, a lot of work is ongoing. And of course, this slide is not comprehensive, just shows some highlights, what's ongoing with CAN, but there's a lot of other work ongoing. And if you're interested, just join the group. You will see everything on our website. A good meeting point of the CAN community is the International CAN Conference. The 19th International CAN Conference will take place from the 3rd of March to the 5th of March in Tutzing in Germany. It's a very nice area in the south of Munich. And there's still the possibility to take part as a tabletop exhibitor. There's still the possibility to become a sponsor of the event, to highlight oneself as a CAN expert or the company as CAN solution provider. And finally, there's still the possibility to become a speaker of this event. So to present as a CAN expert, the how to overcome latest challenges or which kind of challenges you have figured out to the audience and to discuss with experts. So you see a lot of topics are addressed here, and please feel free to submit your abstract to Canon Automation Office. You see here the call for papers is open till September 15th. Yeah, Canon Automation is still a growing community. We have at the moment about 721 members. So a lot of companies still think it is attractive becoming part of this community or being part of the CAN community because the CAN bus is still an attractive candidate for their embedded networks as it is robust, reliable, and very simple and flexible to use. And we see here how our membership is assembled. So we see most of our members are from German-speaking countries. So this might be because the activities are mainly based in these countries. The drivers of the developments are located here in the majority, and maybe also the type of marketing which CAN Automation is doing is a little bit German style. So all of that may cause that we have a lot of German or German-speaking members in our community. Nevertheless, the company language and the language of the association is English. So we want to be an international organization. And in any meeting, if there comes something up, everything is discussed in English so that we can include all the parties, all the experts, and can discuss in a very friendly style. Who is member? Mainly our members are device suppliers, system and subsystem suppliers. Others are diversified from technology enablers such as semiconductor manufacturers, tool providers, and so on. And on the other hand, you see the specific application fields where our members are from. So CAN had been developed for the main use in the road vehicles. Now we distinguish already between road vehicles of highway vehicles. Nevertheless, you see CAN is already used in a very broad range of application fields, almost anywhere where something is to be automated. You will also find someone who is using CAN there. And this reflects also our membership. We have members from all the business fields, all the markets. As I've said, Canon Automation is doing a lot around the CiA specifications, development and maintenance of CAN specifications with the objective to ease the usage of CAN in a certain application field, in a certain device, to give devices a certain degree of plug and play capability. So all this we are doing together with our members. And then around that, we are doing some kind of marketing. We provide marketing services like joint presences at certain trade shows, like the Bauma, where we show as an entire community why it is reasonable to opt for a CAN-based solution, what are advantages for device designers, system maintainers, and so on. If you want to be part, then you have to be a CAN Automation member. We do some marketing by our publications, like the CAN newsletter, where we provide latest insights about overcoming technical challenges in CAN-based networking. And on the other hand, we offer consultancy services, education services, testing services, and so on. I don't want to go into too much details. And finally, I show you where is Canon Automation active, in which areas we are doing some specifications. Today, in this technology day, we are mainly focused on the tasks of the IG lower layers, dealing with lower layer issues. Lower layer summarizes more or less or covers more or less the physical layer issues, data link layer issues. But we have, of course, members that are more in higher layer protocols, device design, how to set up CAN in certain application fields, dealing with restrictions derived from these application fields, environmental conditions, demands with regard to safety, security, and so on. You see here the full picture. The current picture is always provided at Canon Automation website. And in a similar way, we do this with joint marketing, that we try to bundle the forces and say, okay, can automation member want to open a market, maybe in a certain country, in a certain region, overcoming language barriers and so on, or providing technology to demonstrate an entire ecosystem, like we do it for CanXL, to provide image videos, organizing event series, webinars, and other events. So I invite you become part of the CAN Automation Association, become an active member of this group, and to widespread the knowledge about CAN, we are organizing events like this year today, since Corona. People are more and more used to online events. It's sometimes a little bit tricky because we are not really in a physical contact. So you see now my face, I'm talking, but I have not really a clue who is around in the audience. Nevertheless, once again, warm welcome to this event. And I'm going now to present you with the first session, the three CAN protocol generation options that we have since 2024 internationally standardized. Yeah, so in the early 80s, the CAN had been developed and was presented on an SIE conference in 1986. So you see here the press release. And from this day on, the CAN started its success story. So Bosch and Intel announced the joint development of the electronics for automobile networks. And very soon we saw the CAN is a success story in the automotive world. We have today almost no car where not a CAN bus is installed. Very soon the CAN propagated through other markets, so to the trucks, to the commercial vehicles, but also to other markets like farming equipment, like construction machineries, building automation, medical equipment, and so on, as I've already shown when I showed you the business fields of the CAN automation members. CAN is more or less anywhere. And the CAN, organized as a controller area network, as the full name says, was very sufficient a long time. But then they're coming up more and more new requirements with regard derived demands to data throughput. And then in the years about 2010, 2011, there it was the demand, okay, we need to do something with regard to data throughput, for example, for flashing the cars or something like that. And then the development of the CAN FD was started, and the CAN FD was then added to the um, international standard ISO 11898-1 and 2. There were also deep discussions where to add. And finally, we updated these international standards, or they were updated, let's say that way. And we have now in 2015, or we had now in 2015, standard that described the classic CAN and the CAN FD. And when we more or less finalized this job, then there came already new requirements. So I think the velocity while things is changing, demands are rising, is increasing more and more. And we were just finished with the KNFD, and then there came already further requirements that, well, why is there a possibility to further increase the CAN to bring more functionality, more data throughput, and some other features? And then this output of that was the CAN XL, which is now also part of the ISO 11898 1 and 2, once again split with the physical layer and the data link layer description. So we see there was or there's a constant development in the CAN to keep the CAN meeting the current requirements to embedded networks, starting at the SIE conference in 1986, while the Bosch CAN specification 2.0 AB which was submitted for the international standardization, reorganized in 2003. Then in 2015, at another milestone, the standardization of KNFD. And finally, we have the KNXL since 2024 with a small add-on, the KNFD Lite, a small tiny form of KNFD that addresses small, lightweight implementations of KNFD. So let's have a look to this path through the history. What were the requirements? Where were they derived from? So when we're talking about CAN Classic, then we had in mind the typical network architectures where we had some CAN networks, one for body electronics, one for the drivetrain, or two tailored to the requirements, then supported at the lower end, maybe by LIN for multimedia. We had maybe a MOST or something like that, and all were coming together then in a central gateway. So a typical network-oriented approach, as it was very typical for the automotive industry in the first decade of this century. But then there was a shift to something that we call a domain-oriented architecture, where we have already several networking technologies complementing each other in one domain, in the body electronics, in the chassis electronics, powertrain. And there we have, for example, the CAN together with the FlexRay, where we demand more deterministic behavior. We have high-speed communication, automotive Ethernet communication between the domain controllers to update the process image. On the lower end, CAN might be complemented by LIN. So we see here a shifting in the architecture of the car makers. And with that, we see also a higher demand in communication. So there, some Daimler engineers showed us at these ties a slide where they say, let's have a look how the communication developed in the cars. And we see in the late 80s, early 90s of the last century, there was one CAN network inside with 7 ECUs networked, and they were sharing less than 100 messages. And the next generation, we had already 3 times of networks, about 4 times of ECUs, and the messages roughly doubled. And then we see how the amount of data for being communicated increases. We see the number of networks is not doubled, the number of ECUs is not doubled, but the amount of messages that need to be communicated explodes. And this trend is ongoing and is, of course, further accelerated by requirements like AI communication, security communication, cloud-based networking, and so on. And this means these were the beginnings, and the automotive industry said, okay, we have to do something. And one option would be, why not trying to open a little bit the canvas? And then at Bosch, there was the development, and they said, okay, how can we increase the communication speed in the CAN-based network by keeping most of the attributes that we like so much in the CAN, the simplicity, the robustness, and the simplicity of a CAN network design is derived from the fact that you don't deal with any node numbers. You just adjust the priorities of the CAN messages, respectively the CAN identifiers to the CAN messages, and then you plug your device to the network, and according to the priority, the data ranges in the data flow, and you don't have to worry too much about system design. Very simple. But this mechanism is based on something that we call an in-bit time response. So this means within a bit time, the device tries to write a bit and then gets in the bit time the response, hey, I have a higher prior message than you. Please slow down, wait till I have transmitted my message and try then whether you can send your message afterwards. So here if we don't want to shift the nature of CAN, we can't do anything. We are limited to that, what we know with regard to the communication speed from CAN Classic. But after that, we go into a kind of free transmission phase. We don't have any in-bit time responses anymore, and we can open up the transmission speed to that, what our physical layer is capable to drive. And this means we can increase the speed to whatever here in a test under laboratory conditions with non-optimized CAN transceivers. We saw that there were up to 15 Mbit possible. Don't take them too serious. It's just under laboratory conditions. Nevertheless, we see the statement is true. We can turn up the speed up to what our physical layer is capable to drive. And after that, we have once again an in-bit time response. We have the acknowledgement. So we have the same limitations that we had at the beginning. So we once again call the arbitration phase, the conditions. So at the beginning, at the end, we have a kind of wrapper. And here we have the bit timing restrictions. In between, we have the possibility to open up the speed. And this is the basic approach of KNFD. And to make this more sufficient, we also lengthen the data field. So the data field has now the possibility to carry up to 64 byte, and all the rest of the look and feel remains more or less identical. So we have a sufficient way to efficient way to transmit a lot amount of data, and we see it here. The look and feel is almost the same. We have the very same bit fields. Of course, okay, we have here a few bits more. We have the larger data field. We have a little bit longer and optimized CRC, but that's it. The principal behavior of CAN remained equal to classic CAN. And we see here we can tell our controller somewhere in the control field, hey, we want to use the accelerated communication speed. That is what makes CAN really flexible. It's not that we have a certain uncertainty in the communication speed, but we select prior or during the setup of the network, what is the arbitration phase bitrate and what is, in case of doubt, if we switch the bitrate that we are using during the data phase all over the network. So it's flexible for the system designer, but when the system designer has decided, then we have exactly two bit rates. They are adjusted all over the network. And we see here what we can achieve. We have already something what I will talk about in the second talk, the scalability. We can have now two screws. We have one screw, it's the speed which we can turn. So we can turn up the speed in the data phase. We can already gain from that. If you see here, if I turn from 500 kilobit up to 4 Mbit, I can increase my average bit rate up to 1.4 Mbit roughly. And if I increase the amount of accelerate bits, or in other words, if I lengthen the payload, then I can, of course, achieve higher average bit rates, approximately in this example, 3 Mbits. So if you want to have more details, go to the paper from Florian Hartwig of the 13th International CAN Conference, available at CAN Automation's website. Yeah, we have now the option to increase the data throughput in CAN-based networks. That helps us, for example, during flashing ECUs in the cars. And you see here the milestones of the KNFD development. So we had in 2011, that was the beginning. In 2012, we started here at Canon Automation, and there was the demonstration of the KNFD at the International CAN Conference by Bosch. And there was one incident I like to emphasize. There was some problems in the CRC, in the mechanism the CRC was calculated, and this was removed after February 2013. Unfortunately, some early bird implementations were already in the field and are still in the field. To differentiate them from that, what is then finally standardized in ISO, we call it non-ISO KNFD. I will show you later on the difference between ISO and non-ISO KNFD. And since 2019, 2020, the KNFD is in the cars. KNFD is now on the road. So there was in 2025, so last year, for example, the announcement by Bayer Automotive that they saw the Audi Q6 e-tron as the first vehicle with only CAN-FD networks in use. So they substituted all the classic CAN networks by CAN-FD for being faster and more efficient in the data transmission. So we see KNFD is on the road, not only at Volkswagen, Audi, but also at BMW, which were very conservative with regard to KNFD usage. They said, no, we go all Ethernet. Also, they are using in several car series KNFD, not only one, but several networks, also Daimler and others. So all of the OEMs say, well, why not making use of a higher data throughput? Why not reusing knowledge that we have already gained from classic CAN? And by the using CAN-FD, we can allow a faster flashing of the ECUs, can save cabling, reduce costs and weight. Let's have a brief rush through the CAN-FD frame. What was changed? Why do we have more bits? So we see we have 3 additional bits in the control field compared to classic CAN. We have the FDF bit showing that we are now in the FD frame format. We have the BRS bit that allows to distinguish, do we like to transmit the data field in a faster speed, yes or no? And we have the easy bit, the error state indicator, which informs us, is the transmitter of the data in error active or error passive state. So it allows us on a first sight a qualification of the network. Is it in a good shape, or for whatever reasons we see a lot of error frames. Astonishing maybe on a first sight is that we have just 4 bits for the data length field length indication. And the miracle is solved by that we see, okay, we have no longer a counter indicating the size of the data field, but we have a real data length coding. And we see we increase the data field in certain steps. So from 12, 16 up to 64 bytes length of the data field. This is one way you can do it, but you have to have it in mind that it works like that when it comes to working on a higher layer protocol base, that you cannot just send the frames that you really need, but you have always to fill up to the next supported frame length. So this is there sometimes a little bit tricky to make sure that only intended data is transmitted and not just some rubbish that is occasionally in your memory cells. But you have just to be aware of that, and then you can deal with it. Furthermore, we have here the CSC field. Of course, we have an optimized CSC for data frames up to 16 byte. We have the 17-bit CRC, and we have the 21-bit CRC for the all the longer frames, with the intent for increasing the reliability or keeping the reliability of CAN as high as it had been for CAN Classic. Due to this CSC issue, which came up during CAN FD development, there was the stuff count field integrated. Some details you see here. You count the amount of stuff bits and give it in a specific coding. And this allows you overcoming some CSC issues that had been in the early bird implementations. So if you want to make sure that you have operating with the ISO CAN, which you should do, then make sure in the data sheet that you have a stuff count in your CAN FD frame. Due to lack of time, we don't go into further details. If you need some further details in CAN FD node and system design, then I like to point you to the CiA 601 series. So we have there a lot of documents with recommendations and information with regard to that topic. But the development of CAN did not stop at this stage. We see the architectures in the automotive industry were changing rapidly, now more and more to a zonal architecture. You have now zone controllers distributed in your car, and then you collect everything that is occasionally around a zone controller, and you update the process images in the zone controllers in your car, and do something what you may know more from cloud computing or something like that. So the data you're collecting is not necessarily intended for the same kind of application, and needs to be classified somehow under which condition, for which application, in which area was it taken. So a lot of metadata is required, and this means we have further requirements with regard to embedded networks in general and CAN-based network in particular. Furthermore, they are not always very complex, sophisticated devices around such a Zoom controller, but maybe also very simple ones, like those required for light control, for LED control. And with that regard, there were in particular at ST some thoughts, why not enabling here very simple implementations? And they um, proposed a deviation from the CAN-FD with a full extent implementation to a CAN-FD with a lightweight implementation. Therefore, for the application field light control, they were thinking, why not introducing something that is called CAN-FD Lite, a lightweight implementation of CAN-FD, and setting up something that we call a commander responder protocol, that we have more or less a full KNFD device as central controller, as commander, and this commander gives the commands to the end devices, very simple, with very limited resources equipped responder devices that just apply the received values to the outputs, which kind of light pattern should be applied. So I think it's just worthwhile that you know something like that exists. It's also part of the ISO, a very lightweight implementation of KNFD that enables not only light control, but maybe also used for battery cell control or other applications where you have the task to control simple devices where you have only a limited amount of resources supported. Coming back to the requirements derived from zonal architecture, which paved the ground for the KNXL development, there was the demand that we have scalable networks, so that we have the possibility to scale the network with regard to their requirements, bitrate, data links, etc. So if CAN comes then as an embedded network to the stage that it serves as a kind of backbone network, it should also capable to integrate legacy approaches. So maybe you have approved subsystems approved with regard to safety, security, whatever, then you want to keep them. Don't want to touch them, but you want to interact with them, and therefore you need some kind of integration of these legacy systems, and the embedded networking has to have the capability to for that. And furthermore, you have to keep the robustness, even if you have now lengthened frames. And you have to run also multiple higher layer protocols derived from the integration of legacy approaches, for example. And as typically you're connected to the cloud and everything what is outside in the cloud is Ethernet based, you have somewhere a connection point to Ethernet. So you have to think about how can these two communication techniques complement each other, for example, in terms of tunneling and mapping of Ethernet frames. And finally, you want to have source stacks from multiple sources. Therefore, you want to test them. Therefore, you need to have standardized tests. And the prerequisite for having tests is that you have specified and standardized something. So you need open standards. And to allow the interoperability between these multiple source components, you need interoperability tests. And of course, at the end of the day, you want to have these components available from several sources for reasonable prices. And having all this in mind, we developed now at Canon Automation, together with our members, the lead of Bosch and others, the CanXL data link layer, which comes with the features fully backward compatible to CanFD. We have an 11-bit CAN ID, which is only called the priority ID. I will show you later on why. Because the addressing is now possible due to dedicated fields. We have a payload that is scalable in a granularity of 1 byte up to 2048 byte and can be very clearly described by the address field. We have the possibility to distinguish between the real physical network architecture and a virtual network architecture via the CAN ID. The virtual CAN ID, which is a network ID. We have the same robustness and reliability with regard to classical CAN, now for frames up to 2048 byte, via cascaded CRCs. And we have still, and we have in addition the possibility that CanXL can serve as a physical layer for Ethernet. So let's have a rough look. What have we done? So you see here the comparison between the frames. You see the classic CAN and the CAN FD in the middle, and they look rather identical. Of course, they differ a little bit in the size, but the look and feel is still very identical. We have for CAN XL at the first side the same look and feel. We have still the same wrapper, the starter frame, the arbitration field, the control field, the data field, the CRC, and the acknowledge. But of course, CAN XL comes with much more functions, and it does not merge any longer priority description of the data in the arbitration field, in the CAN identifier mainly, and then you have the data, but it comes with dedicated fields for certain functionality. You can now control this kind of functionality with these fields, and this makes the management much easier and the description of the data much easier. So we see this on the next slide. We have an increased data throughput up to 20 Mbit. We can achieve with a so-called fast mode. This we can achieve with a so-called fire and forget mode. We will see it later on. First of all, we have the arbitration field where just there resides the priority ID. You only adjust here the priority, and the addressing is then done in a dedicated addressing field to describe which kind of data do you have here inside. And you can also opt whether you do ID-based, source destination address-based addressing. You have the possibility to distinguish between virtual networks, so you can encapsulate certain complexity. You get rid of the dynamic stuff bit issues because you have a pre-phase CRC, which handles all this CRC calculation, taking into account dynamic stuff bits. And then you have an addition CRC, also including the pre-phase CRC for guaranteeing the same reliability and robustness for up to 2048 byte as you had in the past for 8 byte. And furthermore, you can select here higher layer functions like automated bus load control, cybersecurity measures. And finally, we have here the so-called SDT field, which allows you to describe which kind of data do you have here inside. So which kind of higher layer protocol or protocols is or are supported. So a little bit more in detail, you see on the next slide in the Mac frame in the XL format. So all the bit fields, so I think it's too much for the moment, but you see we have here all the details, dedicated fields for all the purposes. One thing I like to emphasize here is a specific bit stream, ADS and DAS, that is dedicated for switching between the arbitration phase and the data phase and back. So this was a little bit tricky and challenging in KNFD. Here we have a dedicated field that gives us some time for a clean switching between these two bit rates. In KNXL, we have always bitrate switching. And to allow this in a proper way, we have these fields. To allow a super speed, a high speed mode of KNXL, we have to do some tricks. One trick is that we have to remove the error indication. So we switch to a kind of fire and forget mode. And if we do so, then and do the error, the data consistency management on a higher level, how is this done, for example, in Ethernet anyway, then we can turn up the speed up to 20 Mbit if we use the dedicated KNXL transceiver. This I will explain a little bit more in the next session. So this means 3 generations of CAN allow us now um, a lot of functionality from very simple sensor actor networks, as we know from CAN Classic, up to more accelerated functionality with staying more with the look and feel with CAN Classic, but a little bit more data throughput, up to a very powerful CAN XL, which is more suited to backbone networks, integrating several CAN deeply embedded networks on an embedded level, allowing support of several CAN-based higher layer protocols, or serving as a connection point to Ethernet and acting as an Ethernet physical layer. Yeah, so much for the moment. As first introduction, 3 types of CAN. We see CAN is a vivid technology. Various CAN users evolve the CAN so that it meets the requirements of embedded networking today and tomorrow. We have an entire ecosystem, as we will see later on in the talk by Mr. Kaploon. We have now dedicated fields that allows a separation of functions and a separate control of the functions, and we can embed CAN-based networks much better now in Ethernet-based backbone control applications. Yeah, so much for the moment. Any questions to that? I haven't said yet, you can, for questions, open the micro, or vice versa. You can also use the chat function. So then I can also consider that. Please. So,
Hello? Hello?
yes, I hear you. I hear you.
So, okay, thanks for the nice presentation. I am Sinan Arraho from Bosch. Uh, I have some quick questions from your presentation. So you were showing that from the CAN XL, the throughput of 20 megabit per second, and sometimes you speak also about the data rate. Is there any difference in between?
Yes, of course. As I've said, the all generations of CAN have the same wrapper, let's say. We have the arbitration field, we have there the arbitration ongoing, the in-bit time response. And this is the same for CAN Classic, for CAN FD, and for CAN XL. And this in-bit time response is the real limiting factor in CAN for the bit rate that is used in the communication. But the idea of KNFD and then also of KNXL is as soon as you have negotiated in the arbitration phase, who is the sender? You don't have for a certain period of time in-bit time responses anymore. And this means you enter a kind of streaming phase. If you're streaming, you are limited with your communication speed just to the capabilities of your physical layer, but you don't have this double signal runtime, and therefore you can achieve much higher bit rates. As I've shown in an experiment we did for 15 Mbit, even with classic CAN transceivers, the so-called high-speed transceivers. But then, when you are at the end of the data field, which you are transmitted now with an accelerated speed, then you have to switch back because there you have once again the acknowledgement. Yes, I've understood your message correctly. Once again, it been time response.
Okay, and there's also you said that we can run as your network allow the physical network. For example, you showed that FD is going up to 15 megabit per second, but on the
This
other
was
side,
under laboratory conditions.
yeah.
So if we have it more in a standardized way, and if we want to be sure that it works under all circumstances, if I drive my system to the limits, then we are depending on the transceiver chip you are using, on the physical layer you are using. We are more limited to 2 Mbit or up to 8 Mbit. It depends. There are a lot of attributes you have to consider in your setup, starting from the device design to the topology, to the used cable, to the temperature range you want to use. And depending on that, at the end of the day, you know what can I achieve under room temperature in my laboratory, in a nice, clean architecture. I can run with my component the 15 Mbit, but don't take them too serious for KNFD, please.
Sure, but there is one thing that, regardless of that, you might be able to push the data rate up. But usually, you have a certificate of the EMC. In that, for example, you are being certified up to 5 megabit per second. This means that even from the time perspective, you are still be able to send and receive data, but because you are certified with the EMC certificate up to certain limit, I just understood it like that. I shouldn't cross it, even if I'm still able to communicate due to
Of
the
course,
mission.
you
And
have to pay attention to your EMCs. It's okay.
okay, okay, then understood. Thanks.
Good. Then, with an eye to the time, I would suggest that we continue with the next talk, and then we could have some further questions maybe during the break or at the end. Good. The next talk is around the CAN network scalability. So, why scalability? What is the advantage? So for some people, scalability sounds a little bit, oh, it's endangering. I'm worrying about the scalability. Other bus systems might be so nice. They say it's exactly that bit rate, it's exactly that length, that topology. Everything is so fine-tuned. But on the other hand, that makes it on the one hand simple, but it limits you enormously if your requirements deviate just a little bit from these settings, you can forget about this communication technique. And this is totally different for CAN. You can scale the CAN in a way that is suitable for your application. And this is almost always true. So you can find an optimization between performance that you need and network length that you need. And of course, you should also have an eye with regard to the EMC performance. You have maybe some islands of legacy devices or vintage devices, how you like to call them, where they are qualified, they are approved by certain authorities. I don't want to touch them, but I want to interact with them. So why this kind of, because of the scalability, I can integrate these kind of devices, these kind of islands in new architectures, and these new architectures can have, in addition to that, further more performant features. So I would like also to use installed and qualified network topologies now with a higher performance. And furthermore, I see that I can introduce with these new functionalities enablers for demands that are upcoming with regard to safety, cybersecurity in existing networks. So finally, I can benefit from the CAN attributes such as robustness, reliability, flexibility, low power consumption, now at a higher performance. And I can adapt always the can so that it suits to my requirements. And that's the nice thing. But of course, it demands that you get at least a little understanding of the can technology so that you know, okay, what I'm really doing, and then can be a very good candidate for you as embedded network. So I've shown you already that slide and said, okay, you see what's possible up to 20 Mbit. We just see here in this slide provided by Bosch and shown on an international CAN conference. They just showed with 16 Mbit in the data phase. I think the benchmark was 20 Mbit. But maybe that's not your requirement. If your requirement is keeping everything as it is, but just introducing a little bit more performance or longer frames in the same network, then you say, I'm fine with some slow speeds or some slow or some small data frames. If I don't have to transfer 128 byte, so why to use CAN XL? Why not using CAN FD or classic CAN if I just have 2 or 3 bytes for being communicated? So this scalability CAN offers, and I have therefore prepared one slide. So at my company Microcontrol, they did some measurement about some CAN frames. For example, how about transferring 8 byte, a 500 kilobit in a classic base frame format, so a classic CAN frame, let's say, and said, okay, we have there analyzed the frame size and it takes about 225 microseconds. Well, if I have to transfer more data, I can do it in a more efficient way. So, for example, I can use now a KNFD frame. A KNFD frame would allow 64 byte of data. This would increase the data throughput because to transmit 64 byte with classic CAN frames, I would need 8 frames. So this means this would save me already a lot of time. So about 1776 microseconds in contrast to 1144 by using exactly one FD frame. I already save some time, gain some data throughput. One frame, of course, it's a little bit longer, contrast to 8 frames. But then I can think about, well, this of course blocks the bus now for this 1144 microseconds. Is this acceptable in my applications? This places latencies on my bus. If this is not acceptable, I can fine tune. I can say, okay, KNFD offers the possibility to transmit the data field in an accelerated speed. So you see here, just a little bit longer from the timing duration to compared to the classic CAN frame. I have now an accelerated FD frame if I use 2 Mbit in the data phase. But also this has some drawbacks. If I'm doing the bitrate switch in the data phase, I have to work very precise. Otherwise, my communication will fail. I have to re-qualify all the network. And now it's up to me as a system integrator to decide where in the scale do I like to be. Do I like to have and prefer the simple network design? Take classic CAN. If I have no timing issues, no problem. All the simple network and device design rules apply. And I take into account that I have a low data throughput. Do I like to use the CAN-FD with no bitrate switch, or maybe just a small bitrate switch, not exceeding the 1 Mbit? Then I have a large payload and still simple design rules can still reuse physical layer, but a little enhanced data throughput. But I place high latencies on the bus. Maybe that's not acceptable. I have a fast reaction time maybe as a requirement. Then I have to opt for option 3, taking into account that I have to precise in my network setup. And CAN gives me all the scalability. Now I have several network classes. Do I like to run with the same bitrate? Do I like to have a small bitrate switch? Or do I have to like a high bitrate switch and a high optimized data throughput? And it's up to me as a system designer. And increasing the speed always has an impact on the physical layer. And if I want to communicate in a faster speed, with a faster speed, then this means I should optimize my network. These are no new rules for CAN-FD compared with Classic CAN. The rules applied already for CAN Classic, but CAN Classic is very, let's say, tolerant with regard to erroneous system design. So I can make almost any mistake and it will work because the margin for failures is so large. And this is that thing that changes for KNFD, that I have almost no margin for making this. I have to work much more precise. I should have small stubs only and linear network, and then it will work more or less out of the box, having some other things in mind. But in the automotive industry and in some other application fields, you want to see topologies that you see here on my slide in red colors, and they are a little bit more tricky in KNFD, and they demand something, some further thoughts. So first of all, let's see, what do I have to consider? So we have in KNFD two bit rates, bit timing, we have the arbitration phase, and we have the data phase. In the arbitration phase, this is that what is considerably identical to classic CAN, and we have to be a little bit more precise in the terms that we should use the recommended bit rates, that we all in the network should derive these bit rates in the best case from the same oscillator frequency in all nodes, have the same bit timing configurations, and a prerequisite that CAN-FD works in case of bitrate switching, the sample point must be configured in all the devices at the very same point. Otherwise, the communication will fail because the bitrate switching in CAN-FD, and this is exclusively valid for CAN-FD, is done at the sample point of the BRS bit, the bitrate switch bit. And if this varies in the nodes, then some switch on an early point of time, other in a very late one, and the late ones, they cannot catch up with the others that switch in the early point, and therefore your communication will fail. Therefore, make sure the simplest thing, you all should have the same bit timing, the same sample point configuration, and then it should work. And make sure that you have qualified transceivers for these bit rates. And with regard to the data phase bit timing, then make sure that you use the very same time quanter as you did use for the arbitration phase configuration, although this helps you getting a robust communication. And don't forget the transmitter delay compensation. So if you exceed the 1 Mbit, then so that your bit monitoring works, the transmitter delay compensation has to be enabled based on measurement in the transmitter. The design rules that you should follow are given here. I cannot go because of the timing restrictions now I have here in all the details, just that you know you have to work precise in KNFD and make sure that all the devices are qualified for the same temperature range, that the sample points are identically configured. Topology, as I've already said, as short as possible should be the unterminated stubs. In best case, the bit timing is derived from the very same clock frequency all over the network. Sometimes this will not work, but then you should play with a prescaler of the bit rate in a way that you end up in the very same bit timing. So then it will get more and more stable. You should have overall the same impedance. Sounds nice, but you will always have impedance gaps and the connectors when you open up the drilling of your cable. And therefore, we will see in a couple of slides there you should use a component that calms down ringing, that might be amplified by all these impedance gaps. And you will learn in KNFD, bits are not symmetric. If you are painting nominal bit voltage levels, then you will see everything is very nice, rectangular, symmetric. If you will analyze your bits in real world, then you will see they are not symmetric for several reasons. And this asymmetry might also cause problems, and therefore you need drivers, so transceivers that have a specified asymmetry and works with very limited or with very strengthened operating limits to allow high communication speeds. This brings us to these physical medium attachment implementations called transceivers up to the again, classic networks. We had there something that was called the high-speed transceiver. Sounds a little bit funny if we know that this one is today the slowest candidate, but nevertheless, it's called high-speed transceiver. And we have seen it can also run at high speed because the high-speed transceiver or the transceiver itself has no clue about the speed at all. It just amplifies the data or translates the signals into the demanded voltage levels. So we see here for this high-speed transceiver can run up to 1 Mbit. And today they are limited at the lower end to 40 kilobit because of the timeout values. But in this range, I can run with classic CAN transceiver, the so-called high-speed transceiver, any bit rate. And we see here the voltage levels are the nominal ones between 2 volt for the differential signal in the dominant case and the recessive signal 0 volt. And for KNFD, there was then the knowledge, okay, the bit time is getting shorter and we have to be a little bit more restrictive. And therefore, there was the idea, well, which kind of operating limits do we need for 2 Mbit or for 5 Mbit? And then in the edition from 11898-2 from the year 2016, there was the introduction of these parameter sets for 2 Mbit and 5 Mbit transceivers. And then there was the idea, well, it's not only, as I've already said, the transceiver determining the bit rate that can be used, but all the attributes of the physical layer determine at the end of the day what kind of bit rate you can achieve. And therefore, in the latest edition, you will not find this these values anymore, but you will just say parameter set A and B, and which one is more restrictive than the other one to allow higher bit rates from the perspective of the device design. And you see, when there was the specification of the CAN FD requirements for the physical layer, also existing other transceiver functionalities were merged to this edition of the ISO 11898-2. There was also the partial networking introduced. There was also the low power mode introduced. So we have now a big bunch of functionality introduced in these CAN drivers. And as I've already said, we have always to fight with the ringing in CAN-based networks. So we drive the signal and the signal might be amplified in all the impedance gaps in our network. And we have the requirement that at the sample point, at a given point of time, the signal has to be at a level that all the devices in the network sample the very same level. For the edge recessive to dominant, so logical 1 to logical 0, that's not critical because this is an active driven edge and the ringing calms down very fast and we have a good signal level. The critical edge in CAN-based networks is the edge dominant to recessive, as here the drivers just release and the voltage level falls back via such a ringing, which is amplified at any impedance gap in the network. and it has to calm down till the sample point. And if the bit time gets now very narrow, very small, maybe the time is not sufficient enough, or if you have some other effects on top, like asymmetries and so on, this time is not sufficient enough, and it may happen that several devices all over the network detect different bit states for the very same bit, and this is of course critical. And therefore, there was the development of something that is called the SiC transceiver. So the SiC transceiver has the possibility now to actively drive, for example, this bus for a very short time, the edge here from dominant to recessive, and therefore the ringing comes down very quickly, and you have also a stable bus level here. But you have also here to pay a price. You cannot use any longer all the available CAN IDs, and except you are accepting that you are limited to roughly 600 kilobit per second. I will say something about that. For the moment, the good news, we can calm down the ringing on the edge dominant to recessive. And you will see here some pictures in the slides. Anyway, you get the slides after the presentations. And we see here some pictures from the International CAN conference. And we see here in this chaotic network, we see, okay, we have here a sender, and we see the waveforms as it is seen from certain receivers. We see here at that one, at ECU11 or ECU1, and we see, okay, here the signal shape is not a good one and may cause errors in our network. And it changes dramatically as soon as we use the CAN-SiC transceiver. So we see here now, nice signal shape. We can run such networks as well. So that what was some couple of slides ago marked in red is now possible thanks to the SiC transceiver. So this brings us back to the scalability. We have now the SiC transceiver that supports the signal improvement. So these SiC transceivers operate similar as the CAN FD or the high-speed transceiver, where with the same voltage levels, they also show a dominant recessive behavior. They, in addition, have the ability to calm down the ringing on the edge dominant to recessive. You might be confused as over my slides, but also in literature, there appears somehow a kind of threshold value that in the arbitration phase, when you use SiC transceivers, you cannot exceed the 667 kilobit. This is not a hard threshold. This is more a weak one derived from, let's say, system design. So if you exceed this bit rate, then the dominant bits may no longer be reliable detected under all conditions in these high bit rates. So there is an idea, okay, you can limit yourself in system design to selected CAN IDs. So details you will see in a workshop that is currently under development at CAN Automation, which CAN IDs these are. And then you can guarantee, okay, I can run up to 1 Mbit in the arbitration phase and no problems with that. If you want to make a detour around these scenarios, I have not the time to go into details, then stay with this bitrate in maximum. And anyway, you have, that's the topic, the scalability. That's just the arbitration phase. This is just the communication speed for the wrapper. And then you can go to 2 Mbit in the data field. And anyway, you don't care that there was a limitation, just valid for the arbitration phase. So we have now the CAN high-speed transceiver, the CAN FD transceiver. We have the CAN SiC transceiver allowing higher bit rates up to 8 Mbit in very chaotic network architectures. And at the end of the day, we have the SiC transceiver, a SiC XL transceiver that allows the super speed mode up to 20 Mbit if I'm supporting CAN XL. So here we have some changes. The CAN SiC XL transceiver works rather identical to the CAN FD transceiver in let's say the SiC mode. But if I want to achieve the 20 Mbit in the data phase, then there starts a communication. It's PWM based between the controller and the transceiver. And the controller tells the transceiver, now change the way you operate, do something else than the usual non-return to zero coding. And we deviate now from this dominant recessive nature as can have to a logical zero, logical one level, both actively driven. We have now a different signal shape. We modify the logical zero and the logical one between one plus one and minus one voltage, represented with this differential voltage here. And we call that the so-called fast mode, where we drive both signals actively in contrast to the dominant recessive behavior, where we only drive the recessive to dominant edge in an active way. So you see this here, we are running out of time, therefore I can only show it a little bit. That you see we have our in the SIG mode, we have our dominant recessive um, waveform. And then when the CAN controller tells, because the CAN transceiver has no clue about the protocol, the CAN controller has to tell the transceiver, now do something else, now enter SIG mode, and then we have the new voltage format, the new waveform, both signals, the logical one, logical zero, actively driven to calm down the ringing, to get rid of these effects. And then I can run up to 20 Mbit, depending, of course, on some other topology effects. And when I'm stopping on the CAN controller side to indicate we are running in the fast mode, then the transceiver automatically falls back to SIG mode and can run in conjunction with any KNFD controller and so on in normal SIG mode. So we see here, we have, with regard to the physical layer, a high scalability. We have the CAN Classic, the CAN FD, the CAN FD SIG, up to the CAN XL controller with the super fast mode. If I tell the transceiver via PWM coding, the go now to this different waveform. And we have a compatibility between these physical layers. All transceivers can operate the non-return to zero coding. Therefore, we can allow mixed operation. And we can also mix with FD control transceivers, the SIG transceivers. So, of course, it limits the performance of the SIG transceivers. But in general, they can work together in the same network as the SiC XL transceivers. So you see it here, shortly depicted, everything the same, the transceiver always in normal mode, and only if the transceiver gets the indication from the controller, now operate in fast mode, it will do so until the end of this indication and then switches back to the SiG mode, to the normal mode. With regard to the scalability, we have not only the problem getting fast, but also getting far. And therefore, we have currently activities, among others, in the IG CAN OpenFD. What can we achieve with CANFD in applications where I need long-lasting networks, like in vessels, trains, elevators, and whatever. And there we see how does a long cable bring some drawback to the signals, to the signaling, which kind of bit rates can we achieve. And there we can also learn from the plug fests that had been. So we see to a certain extent CAN XL and CAN FD are identical. We see here results from the CAN XL plug fest. What could be achieved? By the way, they are provided in the CAN newsletter. So I have no time at the moment to go into depth here. But what I want to show you also, if you have very long applications or applications that demand for long network cabling, then you see the frequency dependent attenuation has to be considered. Because if you run for 400 meters in your network, then you see you have difficulties in reaching the right voltage levels because of this attenuation. And this may also limit your achievable bit rate. So a lot of parameters to be considered in CAN-FD and in this case also in CAN-XL. And the IG CAN OpenFD together with the IG lower layers, they are currently discussing in this sense how to benefit from CAN-FD and CAN-XL in long-lasting topologies. Yeah, I think I have to come to an end. Also, I could talk another hour about scalability on the data link level, on the higher levels, but I think we have to come to an end at this point. You see, we have a high scalability. We have the FD, we have the high-speed transceiver, we have the FD transceiver, we have the SiC transceiver, the CAN SiC XL transceiver, and we have the XL transceiver operating in fast mode. And depending on the mode the transceiver is operating and in conjunction with which CAN protocol implementation the transceiver is operating, from the device design point of view, the device can support from less than 500 kilobit up to 20 mbit every bit rate. And it depends now, do I have a CAN Classic controller, or do I have a CAN XL controller, or do I have a CAN XL controller here with a SiC transceiver, and I switch the error signaling off, and then I can go into this super speed mode and telling the transceiver generate fast bits. So you see high scalability, a lot of parameters for being considered. And one thing I like to show you at the end of the day, because to the physical layer there belongs also the bit timing. And people that are used to use the classic CAN, they are always saying, I'm using 120, 50 kilobit, 25 kilobit, 250 kilobit, but they don't think about the bit timing too much. When you have to adjust in CAN-FD and maybe later on in CAN-XL, the bit timing, you have to be a little bit more precise. And as I've said, all have to derive from the same oscillator frequency, the same bit timing, and the same bit rate at the end of the day. And therefore, in the IG lower layers and IG can open FD, we are currently developing bit timing configurations. And we say, if you want to achieve a certain ratio, between your arbitration phase and the data phase to meet your requirements in the best way, then you should follow this bit timing configuration as recommended in this upcoming document 101 to save or to work here in the device design very precise and to save a lot of margin for something that we call network effects, ringing, impedance gaps, and whatever. The document is not published yet. It's under development for all CiA members here in the call. They have the possibility to join this group and to learn. So here it's for the scalability if you want to stay in bit rates up to 1 Mbit. And here we have something similar if you want to exceed the 1 Mbit in the data phase. So there exist a lot of reasons why you are not keen on exceeding the 1 Mbit, typically because you want to prolong the usage of existing topologies. Nevertheless, you can, of course, for saving latencies, do some jumps. This you will find here. Yeah, sorry for a little bit taking more time, but it's a so comprehensive topic. And anyway, I had to rush a little bit through all this um, to all these topics. So scalability, as I've said, I started with a physical layer, but you can turn it up to the higher layer protocols and the application. Um, yeah, so much for the moment. And I think we have now a little bit shortened break. Maybe we can stay in the time. Then after oh, sorry, there's the talk from Martin, and then we have the break. So just a quick question. Is there any remark to my presentation? If not yet, I would say we shift any questions to the break and open now the door for the next presenter, Dr. Martin Merkel, who presents in the next talk the topic safe and secure CAN communication. And I don't want to delay any further your talk, Martin. Martin is responsible for the technical documents at Canon Automation, has a long experience as product manager at ICSAT, and I think also in his prior life, he was already involved in CAN-based communication at CERN. So, Martin, please show a little bit from your expertise with regard to safe and secure CAN communication. Thank you for the moment.